First of all, let me congratulate our friends. It's a very good mathematician, Ted, Gabor, and Andre. I know you many years. I remember, for instance, like with Andre, we've been together 1993, right? It was Smith College, right? I remember. And I met Ted also, like 15 years ago, 14 years ago. And I believe, he's a very good mathematician as well as he was a great chair in this department because he invited, it was one of the center actually for discrete geometry. And also Gabor, Feistot, I believe he's a very good mathematician. I like especially his review talks, as well as he's very gentle, very polite person, very light person. Once you remember, we've been in mountain, the four of us. Also, we have some not only mathematical, also some other achievements. Okay, let me start. Actually, this talk, I discussed the subject many times with different people. I remember, like with Carl, we discussed. You remember, like I don't know how many years, 10 years ago probably, to start this project, how to prove the densest packing conjecture in 4 dimensions. And the last my discussion was 10 days ago with Tom Hales. And so I said, okay, during class, say 10 years, maybe 7 years, I said, okay, next month I will start this project. Next month. And unfortunately, fortunately, I don't know, many other things, interesting things I had to do. And finally I decided, okay, I have a good opportunity, very good audience here. Maybe I will present some ideas. Okay, let me start from briefly. Marina already did that, some introduction, but my introduction a little bit different from her. It is a very old problem about sphere packings, and the first is a known Sir Walter Raleigh. He asked this question: how to pack cannonballs in the end of 16th century. He has assistant. And he asked him on Harriot, and he asked him how to pack. And Tom Harriot solved the problem. He found solution. Not mathematical solution, practical solution, and he discovered that the density is pi over square root of 12. It's approximately 74%. This is famous FCC packing. But as you know, there are infinitely many different packing of the same density. Next story, it happened when Kepler wrote this short booklet where he discussed several problems, as well as he considered also this density of sphere packing in 3 dimensions. By the way, he actually had any reference because he received from Harriot. He received several letters, but however he never referred these letters, and he used these letters. But however he never referred these letters from Harriot. So this maybe better to call this conjecture Harriot-Kepler conjecture. It is a part of Hilbert problem. It's, you can see what is written there. It's after 300 years, almost 300 years, so it was still open. But Hilbert saw, it is also well-known story that Hilbert thought that maybe it will be solved very, very soon. Because in 1900 he thought that maybe we'll adjust. And so he generalized this problem, and now it is actually, I don't think it can be solved very soon. Next story happened after Kepler in 1694, even known day, May 1st, 1694. It is a famous discussion between David Gregory and Isaac Newton. They discussed the kissing problem in 3 dimensions, and Newton believes that the answer is for kissing number is 12, and Gregory is 13. Here we have the configuration. When we have a 12 billiard balls, around center one of the same radius, where center of position of centers are vertices of a regular icosahedron. Here, but here you can see some gaps between them. That is why probably if you may be feeling like if you move all of them on one side, maybe there are one place for the certain sphere. Okay, the first proof for sphere packings appeared in 1831, given by Gauss. Beautiful proof. Namely, he proved. I mean, if you translate from he considered quadratic some quadratic forms, but however, it is if you translate it, he proved that FCC that the FCC packing is a unique lattice sphere packing for the, is the best sphere lattice sphere packing in dimension 3. The proof is it's only 40 lines. It's very elementary and nothing complicated. And so many mathematicians try to find something hidden. Maybe there is something hidden, something behind that. And you can see this list of several people. The last publication, by the way, as I know, like it is Mahler by 1992. And actually it's still not clear. Maybe not exists something deep behind that. And succeeded two Russian mathematicians, Korkin and Zolotaryov, succeeded to find to solve the problem for high dimensions, namely for dimensions 4 and they solve the problem about the lattice sphere packing, best lattice sphere packing, and for dimension 4, it's about dimension 5. It is D4 and D5. And between them, there is one more publication, 1875, where they made a conjecture about dimensions 6, 7, and 8, namely E6, E7, and E8. And this conjecture, Korkin-Zolotaryov conjecture, was solved by Blichfeldt. You can see this 1925, 1929, 1935 for dimension 6, 7, and 8. And after that, many publications. The first proof published. Actually, they announced 2003, but it was published by Henry Kohn and Abhinav Kumar. Namely, they proved that the Leech lattice is the densest lattice packing in dimension 24. And for general packing, it's Marine already mentioned that. Mentioned, actually he has two presentations, 1890, it's later, beginning of the 20th century, I don't remember which year. And he claimed that the hexagonal lattice packing is the densest of all possible circle packing in the plane. However, his proof it was not incomplete. In only Last Lefebvre published the first rigorous proof for that. Moreover, as I remember in his book that appeared in 1953, it contains at least 5 proofs, right? Not only one, several proofs. Okay, now there's modern. This what happened after that. In 1998, Tom Haynes announced the proof of Kepler conjecture, and it was published. I don't remember like what it is, 2005 probably. And just recently, less than 3 years ago, it was some automatic proof checking. I mean, so it is now. It is become proof because when it's published, and Gabor was he was the chair of this committee, right? And you decided, okay, it is almost you believe that proof is correct, but however, it is you're not able to check this proof. And Marina gave just a talk, and it is beautiful. I believe it is beautiful, really beautiful proof, mathematical proof in dimension 8 and 20 and 24 with Coulter, with Henry, Abhinav, I don't know, Steve. What is his name? Steve and Danilo, right? Yeah, it is. It is actually. It was expected. I cannot say that not unexpected. It was expected, but however, it took from 2003 till 2016, 13 years, and came from unexpected field because for modular forms. Okay, just let me briefly say something about it's about Kissing number. The first proof had appeared after after several mistake proofs, and the first appeared in 1953, and Schutte and van der Waerden proof the Kissing number problem is a certain sphere problem in the Kissing number problem dimension 3, and however. Leach published a very short problem, but however, his proof, it's nice proof, very interesting proof, but however, it is contains some gaps. And here you can see that from first edition, the first edition of proofs from the book by Agner and Ziegler, that contained also this proof, Leach proof, but however, it was removed. After in the second edition, what is written here, because it is not like complete. And after that, it's also interesting because several publications, and Karol Berezovsky, for instance, published paper 2003 and 3 more. Actually, I believe that Hiroshima Ihara. It's elementary proof. And I believe it is probably the best one. I also have also published the proof, but it's based on the densest method. But I'm still think this maybe to find something more better than we have. It's one of the oldest problem in mathematics. However, we still have no such proof that we can. Teach students, to present for students. Okay, the next dimension is dimension 4, and for dimension 4, the answer is known. A conjecture is known like from 1872, and the Kissing number also is known from 1872 by Korkin and Zolotaryov. The answer is it's located we have it is we have the 24 cell. The 24 cell is very easy. You have 4 coordinates. That will be 2 coordinates 0 and 2 positive or negative 1, plus minus 1. And so we have altogether 24 points. And these 24 points form are vertices of the 24 cell. And so the solution is, the conjecture is that the solution of the Kiesling number problem in dimension 4 is the 24 cell. Here we have some projection of the 24 cell. It is a regular, we have 6 regular polytopes at dimension 4. The most beautiful, I believe, is the 24 cell. You can see here this famous statue by Adriano Agnano in Penn State. It is a stereographic projection, by the way. It is conference room here in Penn State. I remember like only once, and I didn't show this. I mean the 24 cell because it was next door, and all of them they know that. Okay, I prove it is by combination densest method and irreducible contact graph methods. The combination give a solution of the Kiesling number problem, namely that the Kiesling number is 24. But actually, I proved that it is not equal to 24. I proved that it's less than 25. I'm explaining why. I give it a little later a table. So the status of Kiesling number is the following. Now it is known only for these dimensions, 1, 2, 3, 4, 8, and 24, but it is not complete for dimension 4, because we have no uniqueness. It is just question, only conjecture. The solution is unique, and is 24 cell, and the 24 cell, it is like it is roots of D4. Let me a little bit later I defined. Yeah, 3-dimension not unique, yes. Not unique. Okay, it says about uniqueness, it is known, it is conjecture, I believe you know it is, we checked, actually it is in dimension 2 is unique, in dimension 4 is unique, dimension 3, 5, 6, and 7, not unique. Dimension 8 and 24, it's unique. But it's different because in dimension 3, it is a family. Yeah, there are like, but in dimension 5, only 2. In dimension 6 and 7, so also. Okay, let me briefly give some methods. What methods we have to solve the problem if you have like sorry, just let me previous slide. Actually, it is if we have this problem can be reduced for packing a sphere by spherical caps. If you have a unit sphere, then for instance the Kiesling number problem asks how many what is the maximum number of spherical caps of radius 30 degrees can be packed on the surface of a sphere. And the method for that, not so many. Namely, the first method it's appeared in 1943 by Laszlo Festod. It's a so-called Festod bound. That it was extended by Coxeter in 1933, but it was only it relies on some conjecture about the densest packing. It was solved only 15 years later by Borowski. So it is Coxeter. It is called we call this Borowski-Coxeter bound. But the second one, we will consider today second and third one, I mean briefly. The second one, it is a very old method. It is irreducible graphs. Schouten van der Waarden invented that. And Dancer actually some improvements. And Leach actually used it a little bit different, because Leach, he considered also graph, but he not only contact graphs. It is also, he considered some distance graph that's for it not, I mean, not exactly, but also for some just between two numbers, between 30 degrees and something like, I forgot some more. And actually the most powerful method for that, and also it is linear programming, which appeared first by Delsart, Kabatsky-Levenshtein, 1978, Adlishkin, Slovan. Sorry, it is wrong. Kabatsky-Levenshtein, 1978, but Adlishkin, Slovan, 1979. Sorry about that. And Christine Bashok and Frank Valentin, they developed new method, a new algorithm for using semi-definite programming. 2000. Actually, it first published. It was appeared in archive 2006, but it was published 2008. Let me give you this table. Some numbers. I forgot about also to add what Coxter had for this for dimensions. I don't remember exactly, but his number is 26 something. Because he proved that the Kissing number is less or equal to 26. The Kissing number in dimension 4. LP bound gave Abdiscus Sloan has the same number, 25.558, and moreover, Aristov and Babenko found the best polynomial. They proved that it is the best polynomial for the Delsart method, and my method gives better number, but it's still big one. 24.865. Actually, I never interested to have the minimum, but I remember that after some experiment, I found that it will be like 24.60 something. In the first paper, this original paper by Bashok and Valentin, there is polynomial, but not like one, it is like not univariate polynomial, not one variable, 3 variables, polynomial of degree 7, and this polynomial, this method gives this number, but still far. But after that, let's look at this one, beautiful. When we increase degrees, 11, 12, 13, 14, it becomes less and less and less. And so 7 years ago, but not 7, like I don't remember when it appeared in archive, maybe 2009. Actually, and we discussed several times with Frank, it will be, I thought maybe soon will be found explicit expression. But nothing happened. And this publication, it's not published. In archive it appeared last year. By Machado and you all this just Oliveira, but he has this another name. It's okay. And this and they consider it includes, but look, it's very slowly decrease, right? It decreases, but very slowly. And when degree 15 and 16, 24.6 and 24.5, 56 and so on. Probably it is converged, but I don't know how. What degrees? Maybe it is, I don't know. Do you have any feeling for what do you have here? So we are waiting, Marina, maybe see we can find. But in this case, this is the 3 variables. It is very complicated. And I remember like I spent some 2007 try to reduce, because I have some improvements, more variables. And I try to, but these improvements, it have many, a lot of, it is 5-variable polynomial. I tried to find that, but number of variables, huge one. I remember like a first mine was some 10,000 variables. It is impossible to use SDP for that. I tried to reduce it to consider some symmetries, but unfortunately I not succeeded. And also, so that was motivation why I started to think about like some different like Borsuk-Ulam theorem, because to find some topological symmetries to prove to reduce number of variables. Okay, so the first step to solve the problem about the densest packing, to my opinion, is the following. The first step to prove the uniqueness of the kissing arrangement. Probably, look, if you look at this polynomial, right, and to use also the method that relies on a reducible graph, probably it gives us. Because we don't need, for reducible graph, we need something that gives us the decreased number of graphs, I mean like number of arrangements. And I believe, if any of these polynomials give us possibility to reduce it. Because if you consider like, okay, let me just do a couple words to say about this method. This method very simple. For any metric space, if we have any metric space and we have any finite subset, this metric set, then we can define the contact graph. The contact graph is very simple. We found the minimum, psi of x is the minimum distance between distinct points. And let us join by h 2 points from x if and only if the distance is exactly equals psi of x. So we have, it's guaranteed that we have at least one h, but however, usually for good packing, we have many of them. Even I have some conjecture, I can give them exact what is the minimum is, but it's not proof. Anyway, and so we try to enumerate that, but for that actually one obvious thing, we don't need consider any of them. Schut and Vanderwaanden invented this notion. What is the shift of a single vertex? That if we cannot move any vertex such that the minimum distance for other points is increased. So just we cannot that. It is in some sense it's a jammed configuration. And in this case, we can consider this graph is called irreducible. And in the Feyerstedt book that published in 1953, there is a chapter where he considered very carefully properties of this irreducible graph, contact graphs, as well as give some conjecture, many conjecture about like in dimension 3. This is Thomas problem, famous Thomas problem to find for a given n congruent non-overlapping spherical caps to find the radius such that it will be as large as possible. In other words, if you consider the center of them, to find the configuration such that the distance between points is as large as possible. This problem is solved only up to n equals 14, and also for n equals 24. But here for n equals 3, 4, 6, 12, infinity means the density, and as well as for n24, it is by the first method, the method using like area arguments. Because Robinson it is also symmetric, more or less symmetrical case, and he extended Feyerstedt bound. But all other, I mean this Shooter, van der Waal, Robinson, our also proof for 13 and 14, the Thomas problem for 13 and 14, relies on enumeration of irreducible graphs, also to consider some properties, using some combinatorial properties. Here, actually, we have experience because we spent I spent 5 years to develop this method. And actually, I not succeeded for mathematical part, only with computational part. With Alexei Tarasov, we published 5 papers and solved that for 13 and 14. Also, we enumerate all irreducible graph up to 11. This paper, right, it's up to 11. And there is also one more publication with Anton Nikitenko. It's about the same problem for torus. In other words, it is for flat torus. In other words, it is for periodic packing. And here, and this actually it is interesting. I still think maybe it is possible to use some also semi-definite programming for that, and maybe to solve the problem for Thomas problem, at least we need to increase. But however, you can see here, I will show you here the one example for toroidal packing when it cannot be solved by SDP. Look, what happened? Surprisingly, for n equals 7, we have 3. We have 3 solutions. It is not unique. This one, first one, second one, and third one. So it is this method. This irreducible contact graph. Gave us possibility to find that. It's found by computer because I surprised. And there are some conjecture, but this is found by computer. And so, like, if you think about dimension 5 and 6, 7, probably I know only one method, just to direct enumeration of graphs. But it will be billion, I don't know how many for dimension 5. Huge number. Okay. Just a few words, I believe you know about that, in 4-dimensional packing, there's still, there's dn, it is actually all integral coordinates with integral point such that sum of coordinates is even. This is self-dual lattice. The Werner cell is as well as like Delano cell, are regular 24 cells. The density is pi squared over 16. It's approximately 0.62. And the conjecture is that the density packing in dimension 4 is D4. You already mentioned 2 times Konelke's. And Konelke's bound gives, like, it is a central density. It's the density divided by volume of the ball, unit ball. It is just 0.13, right? On this one, this number, still far away. And and this paper, Delight, Oliveira, and Valentino, they improve a little bit, but just a little bit improved. Still very far from solution. In dimension 4, we have actually a very strange. It doesn't work. This Delsat method, like as well as SDP, doesn't work. Moreover, there is some paper that is not universally optimal. That is one of reason why we cannot apply directly this method. And so only I'm talking about like the standard method. Of course, like using SDP, and probably it can be proved. For kissing number, but it is. I will show probably also one of possibility how to prove that. Okay. let me just to put a conjecture. The conjecture is, I call this a 24-cell conjecture. It is it's the same as like we have the Diedral conjecture in 3 dimensions, and here we have the 24-cell conjecture. Conjecture is the following: the minimum volume of any cell in the resulting covalent decomposition of P is at least large as the volume of a regular 24-cell circumscribed around unit sphere. So we have here, since in this much more easier, because in the, if you look at the 3 dimensions, actually we have Diedra, I mean this, oh sorry, what is it? We have a dodecahedron as a Voronoi, as the best with the minimum volume, but however it is in FCC has different. Yeah, and so, but in here it's very simple. We don't need to consider like second round, maybe only neighbors. And a method, the method with not so many ideas. The first idea is just to buy direct enumeration. I don't know how many graphs we had. I don't know, like 100 billion. I don't know, many. If you try to, but however, we can reduce number of graphs for that, and probably like using like some geometry method, maybe we can reduce. But anyway, it will be 1,000, because if a health has 5,000, about 5,000 cases, 5,000 graphs, but maybe here I don't know how many it will be, at least several thousand. However, we still have a possibility to find some function, direct function, and use this positive definite method. But I believe the best possibility to combine these 2 methods. I have a couple minutes. I will just let me explain how to extend this positive definite function for Rn. It is, you can see here formulas. This is a multivariate eigenpower polynomials. I considered this in my paper. Actually, it is interesting. I found this. I wrote this paper 2006, and after that, I tried to find some application to solve some problem. But however, it is the number of variables very so big, because if you compare in the Bashok and Valentin, they have used 3 variables. But for next step, it will be, we have this parameter m, right? M equals 0, it is densest method. I mean, this gives us just regular Gegenbaum polynomials. If you give m equals 1, it is Bashok-Valentin. It will be 3 variables, t, u, v. And if you have m equals 2, it will be 5 variables. And so, but in this case, the number of variables is so big. And so, but I'm not succeeded for that. But what is interesting, we can extend. We have, if you have two more parameters, x and y. Here's the definition of the polynomial. That then these polynomials, they extend all of them, all methods, all of them. And moreover, we have the theorem, the same theorem as we have in dimension. Then we have a spherical, for spherical case. Then this polynomial is a positive semi-definite. That means, for any set of points in Rn, this matrix, the metric is this PIM. It is m. It means because of only first m coordinates. We need also we need also the basis, some basis, orthogonal basis, and we can take first m coordinates. And so in this case, this metric is positive semi-definite. That means exactly the definition of positive definite function. Actually, in dimension 4, we have 5 variables. T, X, Y, U, V. T, U, V, it is the same as, if X equals 1, Y equals 1, we have this, it's the same like Bashov-Valentin polynomials. I mean, 3 variables polynomials. X and Y is extra. Geometrically means it is distant from the origin, X and Y. And so, okay, one possibility, I don't know, it is still exists, right? To find solution, to find like explicit expression for that. But if you cannot, even for kissing arrangement, you cannot find, I'm not sure that is possible. But the second possibility to use this polynomial, maybe to extend a little bit this polynomial, what consider it, I showed before, of some degree, say 12 or 14, it doesn't matter. To extend that, I don't think it is too complicated, because probably we have to consider only neighbors, not many, right? Only neighbors, much more easier. Even we cannot not necessarily to prove the 24-cell conjecture. Maybe to use like what Hales did, he considered some functional, right? That is simpler in some sense, because we don't need exactly for this volume argument. And to use these polynomials, and these polynomials give us, they reduced many cases. Maybe will be on just a few cases after to use this combination. Irreducible graphs, irreducible contact graphs, as well as and this positive definite function, this method. Thank you.